So hi friends, today we are going to discuss about energy level diagram of extrinsic and n-type semiconductors. My name is Saitya Pala. I am from the class CSCC section. The topic that we are going to discuss today is from the subject applied physics. So let's go through it. What are semiconductors? Semiconductors are materials which have a conductivity between conductors and non-conductors or insulators. Semiconductors can be pure elements such as silicon or germanium, or compounds such as gallium arsenide or cadmium selenide. In a process called doping, small amount of impurities are added to pure semiconductor, causing a large changes in the conductivity of the material. Extrinsic semiconductors. After some experiments, scientists observed an increase in the conductivity of semiconductor when a small amount of impurity was added to it. These materials are extrinsic semiconductors or impurity semiconductors. Another term for these materials is doped semiconductors. The impurities are dopant and the process dope. An important condition to doping is that the amount of impurity added should not change the lattice structure of the semiconductor. To achieve this, the size of the dopant and semiconductor atoms should be the same. Type of dopants in extrinsic semiconductor. Crystals of silicon and germanium are doped using two types of same dopants: pentavalent like arsenic, antimony, phosphorus, etc. Trivalent valency 3 like indium, boron, aluminum, etc. The reason behind using these dopants is to have similar sized atoms as pure semiconductors. Both silicon and germanium belong to the fourth group in the periodic table. Hence, the choice of dopants is from the third and fifth group. This ensures that size of the atoms is not much different from the fourth group. Hence, the trivalent and pentavalent choices. These dopants give rise to two types of semiconductors: N-type and P-type. N-type semiconductors. An N-type semiconductor is created when pure semiconductors like silicon and germanium are doped with pentavalent elements. As we can see, unbounded free electrons donated by pentavalent plus valence atom. As can be seen in the image above, when a pentavalent atom takes the place of an silicon atom, four of its atom bond with four neighboring silicon atoms. However, the fifth atom remains loosely bound to the parent atom. Hence, the ionization energy required to set the electron free is very small. Thereby, this electron can move in the lattice even at room temperature. To give you a better perspective, the ionization energy required for silicon at room temperature is around 1.1 electron volt. Or on the other hand, by adding a pentavalent impurity, this energy drops to around 0.05 electron volt. It is important to remain that the number of electrons made available by the dopant atoms is independent of the ambient temperature and that primarily depends on the doping level. Also, as the temperature rises, the silicon atom free from some electrons and generates some moles. But the number of these moles is very small. Hence, at any given point in time, number of free electrons is much higher than the number of holes. Also, due to recombination, the number of holes reduce further. In a nutshell, when a semiconductor is doped with a pentavalent atom, electrons are the major charge carriers. On the other hand, the holes are the minority charge carriers. Therefore, such extrinsic semiconductors are called as n-type semiconductor. In an n-type semiconductor, energy level diagram of extrinsic semiconductor. In extrinsic semiconductor, change in the ambient temperature leads to production of minority charge carriers. Also, the dopant atoms produce the majority carriers. During recombination, the majority charge the majority charge carriers destroy most of the minority carriers. This leads to a decrease in the concentration of the minority carriers. Therefore, this affects the energy band structure of the semiconductor. In such semiconductors, additional energy states exist. Energy state due to donor impurity, denoted by ED. Energy state due to acceptor impurity, denoted by E. As you can see the diagram, electron energy is increasing. Electrons move from electron hole to valency band to connection band. Energy level diagram of n-type semiconductor. The energy level diagram of n-type semiconductor shows the figure below. A large number of free electrons are available in the conduction band because of the addition of the pentavalent impurity. These electrons are free electrons which do not fit in the covalent bonds of the crystal. However, a minute quantity of free electrons is available in the conduction band, forming whole electron pairs. Here we can see in the diagram, conduction band contains so many electrons, whereas valency band does not contain much holes. The following points are important in case of n-type semiconductor. The addition of pentavalent impurities results in a large number of free electrons. In thermal energy at room temperature imparted at a semiconductor, a whole electron pair is generated, and as a result, a minute quantity of free electrons are available. These electrons leave behind holes in the valence band. Here N stands for negative material, as the number of free electrons provided by the pentavalent impurity is greater than the number of holes. Thank you.